Okay. Today we're going to go over Chapter 1 material. Let me first begin by reminding you that simply viewing the video and or going to the course website to view the slides is not something you should do in lieu of coming to class. You should come to class to be able to answer questions and to be able to hear and see what's going on. So today we're going to talk about Chapter 1. The material that we're going to cover is an overview of computer programming. We're going to talk a bit about the programming life cycle, the process of engineering software. Algorithms will be a key part of our discussion today. Machine versus high-level languages will only be touched upon. Compilation and execution will be something that you'll all experience in your lab. And I will skip over history, allow you to read that, and move on to the other topics as time allows. I want to remind everybody that reading the chapter is a prerequisite for coming to class on Monday. So you should have the chapter reading done before you come to class on Monday, and you can anticipate very often on Monday I'm going to give you a quiz on the reading assignment over the weekend. So having said that, let's talk about what computer programming is. It is a process of planning a sequence of steps for a computer. Now, we all have programmed before. Most of you have programmed in high school to some extent. Those of you who have not taken programming classes have certainly programmed a washing machine, a recording device of some type, but you have prepared a set of instructions that should be followed by a machine. Now, what we do is not simply computer programming. What we do is we engineer software. So what I'm going to describe for you here is a process of engineering software called, in our book, the program life cycle and its phases. However, in most literature, you're going to see this particular methodology described as the systems development life cycle, because we're not just simply preparing programs, we are in fact engineering systems. And the process of engineering systems is a very innate process, a process that we all go through and have conducted many times in our lives, where we first analyze our problem and come up with various solutions. We implement those solutions, and then we maintain those solutions over time. However, what we're going to see in the next few slides is that this is very much a cycle. This is not a linear process that has a beginning and an end. It is a cycle that continues in a circular manner. And we all see that when we look at systems. Let's take, for example, Microsoft Word. Microsoft Word has come out with various versions. Each version is a product of one iteration in the cycle. It goes from, what do we need as a word processor? Let's develop a word processing software package. Let's put it out in the field, sell it, and have people implement it and use it. Let's maintain it. Let's put out fixes and patches and other enhancements. And then let's come up with a second version that begins our cycle of solving the problems with the first version, implementing those solutions, maintaining them, and so forth and so on. And the process of the life cycle continues until the life of the particular system has been completed. So let's take apart a bit the very first phase in our life cycle called problem solving. And as I said before, this is certainly something that we have done in the past. Whenever we encounter a problem in our lives, we first stop and analyze the problem. We typically ask ourselves very, very simple problem solution questions. Our approach is generally, how severe is the problem? For that I mean we do a very simple cost-benefit analysis. We don't come up with a $50 solution for a $5 problem. We look at the reoccurrence of that problem. Is it a one-time occurrence, or does that problem occur frequently? For example, in our daily lives, we might find that one of our friends has stopped answering our calls, no text messages, no return calls, and we ask ourselves, well, maybe there's a problem here. Let's see if we can analyze it. So our first thoughts are, well, Maybe this person doesn't answer phone calls very frequently or answer text messages in the first place. Not a severe problem. Or maybe this problem has occurred in the past. Maybe last year this time the person did something very similar and it was right around their birthday, which I also forgot last year. So we ask ourselves about those typical reoccurrences of problems, and very often in the analysis phase the key question begins with why. Why is this occurring? Then we develop a general solution to the problem. More often than not, we develop several solutions to the problem. And in our information science discipline, in our systems engineering discipline, we use algorithms to specify those solutions, step-by-step procedures over a finite amount of time to solve a particular problem. There are many ways to express algorithms, and we'll talk a bit about those ways in just a second. We then think through our solution, walking through it, sort of simulating it, in order to verify that our solution really solves the problem. And once we are fairly sure that we have the solution or the solutions that are needed, again, here is our definition of a algorithm, step-by-step procedure for solving a problem in a finite amount of time. Let me stop for a moment and point out that there's some very key parts of this description. One is that there's a finite amount of time, which means that we cannot have a solution that takes an algorithm to run many, many years before it actually solves the problem. We have to have a finite amount of time before the problem can be solved, and oftentimes that amount of time for a problem to be solved dictates the kind of algorithm that we're going to use to solve the problem. By that I mean, let's say the problem is with payroll, and the payroll is going to be run tomorrow. We need a very, very quick solution, and our finite amount of time is very short. Or let's say that the problem is with our retirement fund, and we're 30 years from retirement. Well, we may have a longer time frame for that algorithm to maybe reinvest our stocks or relook at our portfolios or what have you to see if we can come up with a better retirement strategy. So we look at the time limit for our solution to dictate the kind of algorithm that we might apply to it. Now, I've been talking about algorithms, that deal with ordinary things, and I'm going to continue to talk about those kind of ordinary problem-solving algorithms, but reminding you from time to time that the algorithms that we're going to employ in class are algorithms that are particularly related to information-related problems. We'll talk a bit about those as we progress during the semester. Well, here we have an algorithm that's expressed in a fashion of formalism called pseudocode. This algorithm is, of course, how do you start your car? I want you to pay close attention to this algorithm, and in particular how it is expressed, because you're going to have some homework that's going to be due next Monday to write an algorithm very much like the ones I'm going to show you here. So here, without reading this too much, we insert our key, we measure, we make sure that the transmission is in park, we depress the pedal, and we turn the key, da-da-da-da-da. And I want to show you some key parts of this. I don't want to read it. I want to show you here that we have a construct in our algorithm called a selection construct. The selection or branching construct begins with an if statement ordinarily. It specifies a branch in our logic. One branch if the condition is true, and another branch if the condition is false. Here we have a branch for if the engine starts in 6 seconds, then we release the key. If it doesn't start, this would be the true branch. This is the false branch. If it does not start, then we release the key pedal and the gas pedal and repeat steps 1, 2, 3. Now here's another construct that you'll read about in chapter 1 called repetition or iteration or looping. Here we loop back to step 3 and we iterate over steps 3 through 6 5 times. We call this a counter control loop. okay, or iteration that iterates 5 times or up to 5 times. And if the car doesn't start, call the repair shop. Now again, this is pseudocode. Notice that each one of the statements are numbered step by step, algorithmic expression. Each one of the statements begins with a word that's underlined. That's our key word. In most cases, that's a verb. Let's look at another representation of the same algorithm. Here we have the algorithm on one side written in pseudocode, and here we have the same algorithm expressed in a flowchart. Flowcharts are sort of passé these days. Nobody really uses flowcharts very much anymore, but some people still believe that's one of the very best expressions of an algorithm. So as you can see here, the algorithm is a path through our flowchart. This diamond is our branch or selection, and if the condition indicated here is false, then we take this branch. If it's true, we have to go to that off-page connector, which is that 1. That 1 takes us into depressing the pedal, turning the key, determining if it starts in 6 seconds. If it doesn't, go back and do that. If not, if yes, go down to step 2, and so forth and so on. All right? These slides are, by the way, on our course website. They're very easy to get to, and I'm not going to really go through them in much detail now, but I'd like you to take a look at them as you study for the next lecture. So what have we seen? Well, in the previous algorithm, we saw selection or branching. We saw looping or repetition. But we also saw steps 1, 2, and 3, which were just a simple sequence or series of steps, one after another. What we didn't see is a subprogram. We're going to take a look at those in just a minute. This is another way of expressing sequence. You'll see this repeated in our book. So these are just illustrations of our components of our algorithm. A subprogram is a change in the execution sequence. It's giving execution control over to a subprogram that functions until termination, and once it terminates, control is given back to what's called the calling program. So we have a called function that executes and then returns control back to the calling program. Now, here we have an algorithm that many of you perhaps have experienced at some point in time, and that is an algorithm for giving a party. This is not the algorithm, but more the structure of our solution. We call this a structure chart, and it is a result of what is called functional decomposition, breaking a problem into smaller subproblems such that when the smaller subproblems are solved, the larger problem itself is solved. And we see even a further subdivision or decomposition of the get refreshment step into 2 subtasks or subprograms, example, if necessary, to get the food and to get the drinks. So, let me take a second or two for you to take a look at that. Can we cut the video for a minute? And how do we do it here? Stop recording. Good.